Welcome, everyone. I'm here to answer questions on astronomy, anything in the course. It doesn't have to be stuff that you've been looking at recently. Everything open from the solar system to the distant edges of the universe. Looking forward to your questions.
All right. Matthew asks, is space flat or curved? According to Einstein's theory of general relativity, massive objects warp the space-time around them. But what about overall? If objects like these warp space-time around them, then how can space itself be curved?
It's a great question because it gets to the heart of cosmology and also to the heart of general relativity and what it's about. General relativity is a formidable theory. It's beautiful and austere to mathematicians and mathematical physicists. It's a set of 10 partial second-order differential equations, which is used to torture upper division physics undergrads and astronomy undergrads and mostly graduate students. But it is a beautiful set of equations, and when they're packed into their tensor form, it's just one equation, and it really is, what it's relating is the mass energy density in some region of space to the curvature of that space. So it's a geometric theory of gravity, and that was Einstein's amazing insight, to create a geometric theory of gravity. So in principle, space-time, which is a coupled entity, we always hyphenate it in general relativity and in thinking about space, is coupled to the energy and mass in that volume. Now, the most extreme distortions of space-time and the most familiar ones are those when a massive star dies and leaves behind a very compact remnant, like a neutron star or a black hole. So those are approximate distortions of space-time on small scales, collapsed stars. But the theory of general relativity doesn't specify any particular scale, so it's indeed possible for the totality of the universe, billions and billions of light years in extent, to be curved by the sum of all mass and energy in the universe, which, as we know, is 100 billion galaxies to the edge of the observable universe, and a fair amount of radiation too, although in the present day that radiation is negligible in its impact on space-time curvature. So according to general relativity, yes, the entire universe can have a curvature, and the sign of that curvature can be in either direction. It can have negative curvature in 3 dimensions or positive curvature. And the analogies used, since it's very hard to visualize curved space when you're embedded in it, is that of a 2-dimensional surface, where a sphere is a positively curved 2-dimensional surface, and a saddle extending off in all directions is a negatively curved 2-dimensional surface. So general relativity embeds the possibility of curved space-time on a cosmic or global scale, and in fact the solutions to the theory of general relativity to explain the expanding universe included that possibility. Now it becomes a matter for experimentation or observation. Can we see whether space-time is curved on these very large scales? And the most beautiful and elegant experiment to measure space-time curvature on very large scales was done with the microwave background radiation. You've probably seen this speckly map of very low-level temperature fluctuations, all sky, in the microwaves left over from the Big Bang. Those speckles have a characteristic angular scale of about 1 degree. And because we know the physics that produce those characteristic scale of variations at 1 part in 10 to the 5 in temperature, we know what that physical scale was 400,000 years after the Big Bang. Those microwaves, however, have traveled through space and time for 13.8 almost billion years since they were released in the microwave radiation. So we've essentially can think of the universe as a gigantic optics experiment working in microwaves in this sense. And so knowing what the characteristic angular scale of those speckles was very close to the Big Bang, and then measuring them now with our telescopes, gives us a sense of whether those small speckles, which had a characteristic scale of 1 degree, are magnified or demagnified. If the universe had positive curvature, according to general relativity, though just like a lens, just like an optics lens, those speckles would be magnified. If the universe had negative curvature, those speckles, or their angular scale, would be demagnified. So it's a very simple and elegant optics experiment using the entire universe as the experiment. And the result was measured with increasing levels of precision over the last decade, especially by the WMAP satellite and then by the Planck satellite. And the result is very interesting because it turns out that space is flat to within 1%. It's one of the most precise measurements in cosmology. It seems a little disappointing given that general relativity allows for the possibility of curved space-time, that the universe turns out to be a very vanilla universe, probably the most boring possible, where despite all that matter and radiation, global space-time curvature is very modest. Now, cosmologists, of course, turn this argument on its head and suggest that the flatness of space becomes something that we must understand in terms of the Big Bang model, since the universe, we do think, started in a very small, dense, and highly curved state of space-time. But that's the topic for another question.
Okay, so the next question is from Janet. And sorry, let me get closer to the microphone. The next question is from Janet, and she is interested in what exactly the Hubble flow is and how it is measured.
Hubble flow is a technical term in astronomy for the smooth linear expansion of the universe. Hubble expansion is another way of calling it. The word flow is interesting because it makes the universe sound like a big river where galaxies are flowing. Essentially, they're being carried. You can think of the galaxies as sort of stones or twigs on the river of space-time, where the expanding space-time just carries those galaxies ever further apart from each other. So in the simplest view of the universe, the expansion of the universe is homogeneous and isotropic, which means it's the same in all directions that we look, and it's the same at every location that we look if we measure at the same time in the history of the universe. So the expansion rate should not change with direction. Hubble flow is essentially saying that the Hubble constant, or the rate of recession of any galaxy from any other galaxy, is a constant. That rate at a given time in the universe is always the same. So Hubble flow is this smooth expansion rate, but of course the universe is not empty. So while space-time could be expanding smoothly, the presence of mass within the universe will deviate from this, because galaxies are not simply twigs or stones being carried by a flowing river. They interact with each other by gravity. And so we know that galaxies will interact with each other, of course attracting each other, and this will tug them away from the smooth Hubble flow expansion. And this, in fact, has been observed. It was first observed 40 or 50 years ago when we started measuring redshifts for large numbers of galaxies. And we can see the end result of this because when we have clusters of galaxies, which are large aggregations of galaxies, hundreds or maybe even thousands, in one volume of space, those galaxies probably fell into the cluster to produce that large entity. When they formed, and early in their history, they were probably traveling with the smooth Hubble flow, just following the flow of the expanding universe. But because they had mass, they attracted each other, and eventually when they aggregated into one volume of space, they started to pull in outlying galaxies. And so a set of galaxies were essentially detached from the smooth expansion and flow of expanding space-time to become a bound gravitational entity that we call a cluster. And there are smaller examples of this. As you know, the Milky Way and Andromeda are moving towards each other at 100 kilometers per second. And that, of course, is not what the Hubble relation would predict. The Hubble relation should predict that every galaxy is moving away from every other galaxy. So in this case, the proximity of Andromeda to the Milky Way means that they are attached to each other, if you like, by gravity, and so falling towards each other, even though space-time around them and under them is expanding.
Okay, the next question is from someone on the live session, and also this has been a kind of an ongoing discussion in the course. Have you seen the film Interstellar? Is it at all real? And what are your thoughts on the science behind Interstellar?
Yeah, it's I have it in my B list. I don't give it an A, but I give it a B. This could be a long discussion. I'll try and keep it fairly short. Interstellar, of course, had true expert science consultation behind it. Kip Thorne, who is the primary scientific consultant on the film, is a gravitational theorist of extremely high repute at Caltech. I was a postdoc at Caltech, so I met Kip Thorne a number of times, and he's a very nice guy, as well as being a brilliant gravitational theorist. And he is one of the very top gravitational theorists in the world. And he's written popular level as well as technical books on gravity and curvature of space-time and the possibility of time travel and white holes and so on, and wormholes. So he is one of those physicists who's not afraid to speculate because he knows that there are things we know about gravity and things we don't know. Nobody knows what it's like inside the event horizon of a black hole, because no one's been there, and even if they had been there, they couldn't get out to tell us what it's like. So I think in the movie, Kip Thorne was allowing, or he was encouraging the filmmakers to have a core of solid science about how black holes might work and what they might even look like, but then also to take some artistic license. And in my view, the film, of course, does take artistic license. It plays with the situation in ways that are not strictly realistic. And that same criticism can be leveled at almost any film. There's a famous example of this in the movie Contact, which many of you may know, which was based on a book written by Carl Sagan. And Carl Sagan was a consultant on the movie itself. The director was Robert Zemeckis. And the opening sequence of Contact, badly distorts the true situation, because it's this iconic sequence of signals traveling out from the Earth, radio signals and TV signals, as we zoom back from the Earth beyond the solar system into the stars. But they get the timescales completely wrong, because as we move still within the solar system, we hear radio broadcasts from the Second World War, the Civil Rights era, and those, of course, represent light travel times of decades, which would put us at the nearby stars. So that gross distortion of light travel time in the movie Contact was done under the eyes of Carl Sagan, a great astronomer. And I think Interstellar is the same situation. There was a great gravitational physicist who was a consultant on the movie, and some of the artistic license was probably at the edge of the science and understandable, and some of it just went way beyond the science and sort of broke the science. And when scientists or astronomers watch movies, they can be a slightly annoying audience. Astronomers should probably only watch these kind of movies together rather than with civilians or people who are not scientists, because the arguments tend to be a little arcane and maybe nitpicky. Sometimes with a movie like that, and others that have been in the last few years, I just like to sit back and enjoy it. And if it's a well-made movie and well-acted and gripping cinematography and so on, then usually it carries the day for me.
Okay, we have a couple questions about galaxies and colliding galaxies. Why are galaxies colliding now? Why not earlier when they were closer together? Did gravity exist when the universe started to expand? And then we'll go on and talk about how we know we're going to collide with Andromeda and not just get into an orbit around each other.
Okay, good. So it connects to what we were just talking about. So actually, galaxies were colliding a lot more early on, because part of the underlying paradigm of cosmology is what's called hierarchical structure formation. And it's basically a bottom-up scenario where the smallest gravitationally bound objects form first, and they aggregate through gravity into larger objects. So we have very good evidence, indirect evidence, because this is all stuff that happened 8 to 10 to 12 billion light years ago, that the first galaxies to form were small galaxies, dwarf galaxies, maybe even large star clusters. And over time, those dwarf galaxies merged together to form larger galaxies. We know that the Milky Way, as it exists now, was put together from dozens, maybe even hundreds of small pieces or small galaxies. We now, at the present day, have about a dozen dwarf galaxies that are either colliding or merging with the Milky Way. So this process continues. But it was much more active early on. So the simple answer is that yes, galaxies were merging more rapidly from smaller pieces early on, and that process has slowed down substantially as the universe thins out and becomes less dense. So in the old and cold universe, where the distance between galaxies is larger, this infall of galaxies to each other is a more rare phenomenon. That brings us to the Milky Way Andromeda situation. The Milky Way sits in an overdensity of galaxies called the local group. The local group consists of the two large galaxies, Milky Way and Andromeda, and some smaller ones, M33, and a series of dwarfs, perhaps a few dozen dwarf galaxies. And these galaxies are very loosely and perhaps not fully held together by gravity. But that said of a dozen galaxies, most of which are small, in a small region of space, a few million light years across, does constitute enough gravity to keep them in one volume. And because the two most massive galaxies are not that far apart, 2.25 million light years, they are indeed bound, we think, by gravity. That's Milky Way and Andromeda. And at that speed of 100 kilometers per second, the estimation is anywhere from 3 to 4 billion years before they merge. As for those part of the question of Are we actually going to collide as in a head-on collision, or is it going to be more of a gravitational dance or an orbit? That's a little unclear because, of course, all we can measure is the Doppler shift, which is the radial component of the motion. And the motion of the Andromeda Nebula is a three-dimensional motion. We can't measure the x and y components of that motion, just the z dimension. And so you actually have to model the situation. And the simple answer is it's not clear exactly how they're going to come together, whether it's a head-on or a glancing collision or even more oblique. But regardless of how the angle of the collision occurs, the outcome will be the same. If these two objects are bound, then they will very quickly spiral around each other and coalesce and merge. And then more particularly, the massive black holes at the center of each of the galaxies will merge fairly quickly, while the stellar systems that surround them will be disrupted. Arms of stars will be flung far into space. Some stars will be ejected from the joint system. And then the rest of the stars will sort of slowly settle out over a few 100 million years. And that outcome is pretty much insensitive to the exact angle with which we're approaching Andromeda.
Okay, several of the students have interesting questions about black holes. So the first one is very general, and the question is, since even light gets trapped by black holes, doesn't it seem a paradox that black holes evaporate?
Yes, it's a general question, but it's quite a high-level question because it's relating to an aspect of black hole theory that is a prediction that hasn't yet been confirmed, and that's Hawking radiation. So it was originally speculated, back into the 50s, 60s, and into the 70s that black holes were black, or as they, in the jargon of the theorists, hairless, that they only had very limited properties. And the limited properties we thought they had were mass, size, and rotation, or angular momentum. When Hawking came along with his development of black hole theory in the mid-1970s, essentially what made his name and his reputation, he recognized that there might be another subtle process in play that would mean that black holes are not entirely black. And it's called Hawking radiation. So his hypothesis from his theory is that black holes emit a very, very feeble amount of thermal radiation at an equivalent temperature of micro or nano Kelvin. So it's extremely low energy, long wavelength, feeble thermal radiation. But by the equivalence of mass and energy, if black holes are emitting radiation, they're also emitting an equivalent amount of mass, which means logically the black holes are indeed slowly evaporating. So that's the gist of Hawking's theory. The details of it are quite subtle. Basically, in physics, it's known that out of the vacuum of space, particle-antiparticle pairs come into being and then go back out of being. So from the vacuum of space, you can borrow energy enough to make a particle-antiparticle pair, and they disappear on very short time scale, tiny, tiny fractions of a second. And we know from various lab experiments that this is happening, and that these particle-antiparticle pairs exist. Sometimes they can be actualized in the lab, and then you end up making a particle and an antiparticle. And sometimes they're what's called virtual pairs, or just a froth of this evanescent coming and going of particle-antiparticle pairs. Hawking recognized that this process is a universal process, and so it must be appearing near the edge of a black hole at the event horizon. And therefore, logically, there would be a situation where as a particle-antiparticle pair is created, one member of the pair will be inside the event horizon and the other will be outside. In other words, one of the pair is trapped, lost from the universe, and the other is free to travel or continue. And so that, in a nutshell, is the gist of at the quantum level or at the microscopic level of the mechanism by which black holes evaporate and emit radiation. As for testing the theory, it's extraordinarily difficult. We're barely at the level where we can demonstrate that something called an event horizon actually exists, but we're getting close. Hawking radiation, depending on the mass of the black hole, has the temperature, as I said, of nano Kelvin or even less, and there is simply no way in astronomy to measure such a feeble amount of thermal radiation from an isolated black hole. It's not an observation that's on the cards, I would say, even for decades.
Okay, so the next two questions are about black holes of various sizes. Julian is interested in the discovery of a new stellar mass black hole at a great distance discovered this week. Did we learn anything new from that? Do we know how they're formed? And someone else asks about a black hole that was discovered recently that was 12 billion times more massive than our sun. What does that tell us about the universe, and does it change anything about how we think about it?
The distant stellar mass black hole is important. It's actually hard to study. When the black hole candidates, and that's what we call them, because proving a black hole is not something that is easy to do, so we basically have candidates where they're in a binary system, and the measurement of the binary system parameters gives you a probability that the mass of the dark companion is more than 3 or 3.5 times the mass of the sun, which will fit the definition of a black hole. So there's a probability attached to it. And this new candidate is important because we just have very few excellent candidates for stellar mass black holes. Literally less than 3 dozen, and perhaps only a dozen that are really excellent. So that's a small enough number that any new candidate that can be carefully observed is important. This one's far enough away that the observations are quite difficult. But because of the small number of excellent candidates, it's an important detection. The large mass black hole is, of course, fascinating. It's actually been known for some years that nature seems to put a limit on the mass of black holes that can exist in galaxies. There's a very simple scaling relation where the mass of a black hole, which we believe every galaxy contains, including the Milky Way, is directly proportional to the mass of the old stars in that galaxy. And in the Milky Way, which has a lot of young stars in the disk, that old star component is called the bulge. It's that sort of peanut-shaped central region of older, redder stars. So it's a remarkable correlation over 5 orders of magnitude, going down to dwarf elliptical galaxies, which have a very small number of old stars, up to giant elliptical galaxies, which have vast numbers, like 1 trillion old stars. The mass of the black hole scales brilliantly with a scatter of only a factor of 3, which is a small scatter when your range is a factor of 100,000. This new discovery fits that correlation because it's an extremely massive galaxy that seems to have hosted the most massive black hole known. Measuring the mass of a black hole, as I just mentioned, has an error attached to it of a factor of 3. So claiming records in this area is a little controversial, and I would say research groups kind of argue about this a bit, because really what you're saying is that the mass is about 12 billion times the mass of the sun, but the error is probably a factor of 3 on that measurement, maybe a factor of 2 if they did it carefully. So it means actually it could be 12 billion solar masses or 24 billion solar masses. It's not that precise. But let's call it the record holder for a minute. What does that mean? And what does it mean that this was observed a long time ago? So the other important aspect of this discovery is this is a distant galaxy. So this is a very massive black hole that was present in the infant universe, or the very early universe, perhaps within 1 billion years of the Big Bang. And so the importance of this object is not that it breaks the Guinness Book of Records for the most massive black hole. That's nice. The importance of this object is for the theory of how galaxies and black holes form and grow. Because by finding such a huge black hole so early in the universe, you're faced with quite a challenge in theory as to how to grow that black hole quickly. And basically, in less than 1 billion years, you have to grow a 10 or 12 billion solar mass black hole. That's really hard to do because black holes can only grow in the early universe so much by the merger of galaxies and their nuclei. They also have to feed on material, gas, and single stars falling in. And that process will work, but it's actually not that efficient. It's a kind of messy process. So when people look at the theory of how black holes form and grow, this kind of an object, a 10 billion solar mass object so close to the Big Bang, is right at the very limit of how you can generate a black hole that big that quickly. And it's going to challenge theories to explain this. In fact, to do so, people are left speculating that there may have been a seed population of black holes early in the universe, the first generation of stars, which included very massive stars, perhaps 100, 200, maybe even 300 times the mass of the sun. And those very large, remember, a star 300 times the mass of the sun is 100 times the mass of the black hole candidates that we study in the nearby universe. So that sort of kickstarts this whole process of black hole growth. If you have an early seed population of very, very massive stars leaving behind very big stellar mass black holes that can then merge and jump you up through the orders of magnitude you need to get to.
The next question is from Felicity from Udemy. and she asks about moon craters that she was classifying on the Zooniverse project. One feature they were asked to mark was eroded craters, and she found several. But since there's no surface water, virtually no atmosphere, and no wind, how would this erosion occur?
Yeah, it's a good question, and I think the word erosion is, of course, evocative. So I think planetary scientists or people who study the moon sometimes use the word erosion in a kind of a loose way, where they use it to bracket a set of processes that are not just caused by liquid water and that kind of process. So we think that the Earth is obviously has its surface heavily altered by the atmosphere, by water and erosion, liquid water on the surface. The moon has none of that: no atmosphere, no liquid water. So what can make a crater look like it's eroded? It is possible for suitable impacts subsequent to the original crater to give it the appearance of erosion, because those subsequent impacts can, if they happen on the crater wall, say, or the lip of the crater, they can just make it look like it's been eroded on that side, where especially if that subsequent impact happened to obliterate at or near the surface, so you don't see fragments of that subsequent impactor. So you can be fooled, I think, into looking at an erosion-like feature by subsequent impacts. Another possibility is sort of geological processes. The moon is essentially geologically dead, but it's not absolutely totally dead. There are some modest amounts of seismic activity and motion in the moon. It does have some internal heat, and so there are occasionally small amounts of slippage, moonquakes, if you like. And those moonquakes can also be induced by the Earth, which exerts a tidal force on the moon, just as the moon exerts a tidal force on us. So I think a combination of mild geological activity, very mild, and the subsequent impacts on a otherwise pristine-looking crater can give the appearance of erosion. But you're right, there's no other explanation, since there should not be processes of water operating.
Okay, the next question is from, sorry, I misplaced it for just a moment, is from Milan, and Milan asks, I heard that Betelgeuse, the star, will explode someday. How much time is required for this event, and can we see it easily?
So it's an interesting question. People have looked at the most massive and highly evolved stars in the nearby universe, which is to say within 1,000 light years. We see giant and supergiant stars in the naked eye stars like Betelgeuse to much larger distances than main sequence stars or dwarfs, which are mostly tens of light years. So we have stars in the naked eye sky that are massive and evolved, that are distances of hundreds or even a few thousand light years, and they are near the end of their lives. And it's a natural question, since these stars are going to detonate as supernovae, and some of them are close enough to potentially do us harm. It's a very good question to ask, can we make a prediction of when they're going to go off? And so the trouble with this is, for Betelgeuse, as for other stars in this category, we may have a measurement of the mass of a star, which we do, and the mass is, and that allows us to create an evolutionary scenario for this star. We may have a rough indication of what evolutionary stage it's at, but remember that most of the activity in a star happens deep in the interior. We only get to diagnose the nuclear reactions that are taking place indirectly by the amount of luminosity that that star is putting out, and by spectroscopy of the outer envelope of the star. And that outer envelope includes material that's sort of been mixed or ejected from the star, but it's not the current nuclear processes that are underway, because those are deep in the heart of the star and visible to us. So it's very difficult to pin down exactly what phase of nuclear fusion a massive star is at. That's important because in the end of a massive star's life, any star more than 10 times the mass of the sun, the last phases of nuclear fusion occur in a crescendo. Moving up the periodic table from silicon to iron, for instance, the last major transition, literally only takes weeks for the most massive stars. So, and then at the end of this process, you have an iron plasma core, which has no pressure support. The star collapses, detonates as a supernova, and there you have an incredible cataclysm. So the last parts of this process take place very quickly, but our diagnosis of what stage the star is at is much cruder. So even though we know from stellar theory what path these massive stars will take, we can't identify where they are in their timeline very well. What's the precision with which we can identify their position on the timeline? And the truth is, even for the most massive star that really seems to be very near at the end of its life, the precision is centuries, maybe even millennia, which for a star is a very short amount of time. I mean, the main sequence lifetime of a massive star is a few millions of years. So we are able to define its evolutionary state to within 1% or so, which is a pretty good measurement. But a percent of a million is thousands of years, and we would like to know it a bit better than that. We don't want to be told it's going to go off in a millennium. We want to be told it's going to go off now, or in 10 years, or 20 years. So the answer is that stellar astrophysics and the observations that we can make on these stars just do not give us anything like the precision to make that kind of a prediction on a human time scale.
Right. The next question is from Adam, and Adam asks, what kind of roles could so-called citizen scientists take in the field of astronomy? Is it a good avenue for further exploration of the subject?
Absolutely. Citizen science, has been around for quite a while, and of course it's now very pan-scientific. I've seen citizen science projects in archaeology, anthropology, botany, all the life sciences, genetics, etc. But astronomy was really one of the first, if not the first. So citizen science has been around for a while, a couple of decades actually. Didn't get called citizen science for a while. The advantage of astronomy for citizen science is that the data sets are out there from large telescopes. The objects are all remote, so you don't need a lab. And the internet is available to a lot of people with decent bandwidth, so most people can get involved in this. This sort of, the granddaddy or the mother of all citizen science and astronomy was Galaxies, which is still an extremely successful project. The base operations now run out of the UK, but it's very international. And citizen scientists in the Galaxies project, and my numbers will not be current, have classified, I think, tens of millions of galaxies and have actually been authors or co-authors on several dozen research papers, refereed research papers, which is the gold standard in research. So in astronomy, the best citizen science projects like Galaxies not only lead to very helpful work done on classifying millions of galaxies that would be very hard to do and which a machine, it turns out, cannot do very well, but also have actually led to real discoveries into research productivity. That's not why many citizen scientists do it. They just do it for fun, and they're not in it for that long haul or maybe at that level. In astronomy, other very successful citizen science programs involve Stardust was another mission. We're looking for, which had this sort of tennis racket-shaped aerogel to gather cometary material, dust from the outer solar system, protoplanetary material, and it was returned to Earth. And those trails through the aerogel, there's thousands of them, tens of thousands of them. They're very hard to diagnose because they're three-dimensional. And that's another area where citizen scientists have really been helpful in picking through these tracks and classifying them and looking for things that might be interstellar dust particles. Kepler is another example. Kepler is the satellite that's detected exoplanets by the transit method. Kepler data is noisy, and the astronomers on the project, have to push down the noise to dig out these very faint eclipse signals that are tiny fractions of a percent. And once again, the keen eye and the patience and the crowdsourcing of citizen scientists has been useful in discovering exoplanets. And again, citizen scientists have their names on refereed research papers in that field too. So everything from galaxies to comets, you have citizen science and astronomy, and I think it's only going to grow because there are large data sets now from the Sloan Digital Sky Survey. Probably the most extraordinary opportunity for citizen science and astronomy is going to come with the Large Synoptic Survey Telescope, the telescope for which we just finished the mirrors. It's going to go down to Chile, and it's essentially going to take a picture of the southern sky to Hubble depth every 3 days, and then do it over and over again, looking for things that vary or move. And the automated pipelines that are trying to find things from that data are very efficient, but they will miss things. And there are things the pipeline will not be designed to detect. And the project has committed to making the data, the entire data of the project, 20 terabytes a night, if you can believe it, the raw data, available publicly, immediately, overnight, basically. And so citizen scientists are going to be needed, actually in huge numbers, to help with digging through that enormous data set, which will start arriving, we think, in about 5 years.
Right, the next question is from Joe, and he asks, explains that he's still upset about the fact that the US no longer has a space shuttle, but can you discuss broadly why we humans study astronomy? He feels that the study of astronomy is extremely interesting, and he wants to know, regardless of his opinion, what's the gain for humans in studying astronomy and space other than the acquisition of knowledge and ballpoint pens that write upside down?
You're upset about that, and we all, because we were talking about it just before this, we're upset that Spock died. That's kind of hard to take too. So there's always something to be upset about. Yes, the reference to your question, of course, is a big agitating fact of the current space program. So that with the demise of the shuttle, the loss of the second shuttle and its rapid retiral after 135 or 137 missions, I forget the number, has left us in a situation where for 5 going on 6 years, we rely on the Russians to get to the space station. And we're not, as we know, we're cozy with the Russians up to some level, but we're also annoyed at them at some level. So it's not a good situation to be in. As you probably know, the private sector is stepping in here. Elon Musk and SpaceX, who have been ferrying supplies to the space station and have had multi-billion-dollar contracts with NASA to do so, along with Orbital Sciences, are planning their next larger spacecraft, which will carry astronauts. And of course, after a couple of stutter steps and false starts, the US is planning the successor to the original Orion concept, which will be a heavy lift capability that can carry astronauts into high Earth orbit. So the days of depending on the Russians are close to being over. As for why I study astronomy, it's a good question, and scientists all have to defend what they do because the budget pressure is real, and there's some pressure in the United States and in my home country, Britain, and elsewhere to only fund science that yields practical or economic benefits, and astronomy would seem to be at the bottom of the pile if you evaluate your science spending that way. So I think what astronomers do is they definitely hang a lot on the fact that that there is some value to the pursuit of knowledge for its own sake, that understanding the universe, understanding where we all came from, understanding the fate of the Earth and everything around it, our origins, the stories of our atoms in and out of stars. These are profound things that really attach to human culture, not just to knowledge and to science as an activity. And so it's a part of who we are to know and understand these things. It distinguishes us from other fairly smart animals on the planet, like elephants and dolphins and so on. So it's a birthright of us as curious apes that learned how to live and create agriculture and then industrial revolution and then a technological revolution. This is went along with it, the development of telescopes and learning our place in the universe. So that, I think, is always the core argument. The second argument that astronomers use, which applies to all science subjects, is that astronomy is an excellent vehicle for just STEM literacy in general. STEM is the acronym for science, technology, education, and math. And that is an issue of national importance because most of the job growth is in STEM fields. There's a lot of job growth in STEM fields. There's a lot of requirement for STEM graduates. And more broadly, there's a requirement in a technological world governed by science and technology that the average citizen understand these issues. And astronomy is a brilliant vehicle for teaching how science works in general, or how science can learn about the world in ways that we might one day apply, even if we don't know how to now. So I think those two are the core arguments that astronomers would use for their subject, and then they would rely also on a purely aesthetic argument that the sky and the objects of the sky are beautiful, that people appreciate them on a purely aesthetic level as they would appreciate music or art, and that also has value in its own right. As an example of that, when NASA was the previous administrator of NASA, was unwilling to risk astronauts, having lost 2 shuttles, on servicing the Hubble Space Telescope for a 5th time, and was wanting to let it die a natural death. The cacophony of voices criticizing that decision came from the general public, came from teachers and 6th graders and the average person who had an astronomy picture on their screensaver on their computer, who were not scientists. And they just said, you've got to save the Hubble. It makes these incredible images, and I love them, and I use them in my classroom, and I have them on my computer, and I appreciate them. That's a part of my life, and it's a small part maybe, but I don't just lose that for no reason. And really was quite chastened. The administrator was chastened and in the end reversed himself, and the Hubble was fixed for a final time and is still delivering those gorgeous pictures, which are the aesthetic component of why we do astronomy.
So then this next question has some of the most votes on the live session. And so people want to know, we all know about the Mars 1 mission. What are your thoughts about this future mission?
So I talked to, I'm not a space technology expert, but I know people who are. And the people I rely on here are, I go to NASA centers and get many courses and talks, and then we have people in our home building do a lot of high technology work. And let's just assume for now that the people I'm talking to in NASA don't have an axe to grind. It's not like they want Mars 1 to fail because it's not a NASA mission. They want the activity to happen, so they're completely gung-ho for exploring Mars however we do it. But the basic technical judgment of that mission is that it is exceptionally challenging, and that it is probably not going to succeed, and certainly not on the time scale they claim. If you've been following it, Mars 1 is a mission out of Europe. The entrepreneur, and I think he's a very wealthy man, Blas Landorf, was a Dutchman, I think, maybe a billionaire, but certainly very wealthy. He's funding this himself. Has a proposal for one-way trips to Mars, the building of a Martian habitat, so basically waves of, I think in groups of 4, Mars colonists arriving, setting up an initial habitat, and then expanding it sequentially every few years, of growing, of getting everything they need locally, because it's too expensive to bring supplies in. So basically you have to be able to mine the Martian soil for oxygen and water, and they both exist. If you drill down, you'll get water, and the soil itself has oxygen that can be liberated fairly easily by chemical or electrical means. And so there you can be self-sufficient if you do hydroponic agriculture and so on, so you make your own food. So it's a staged approach, but it's a very aggressive time scale, because their time scale is of course set by the closest approaches of Mars, and there's one window they have which really closes pretty hard on them in 2020. And they are still claiming they're going to get their first wave of initial explorers and colonists out there for the 2020 closest approach. And that, of course, is falling on a trip which is 9 or 10 months, I think, in duration. It's probably the most hazardous part of the trip, is the voyage there. So Mars 1 is still talking a good story. They, in a very public and well-advertised way, they've winnowed down from 100,000+ participants down to 1,000. I think maybe they're down into the hundreds now, when they undergo much more rigorous physical testing and psychological testing. What is the impact of isolation? Because these people are going to be isolated, extremely isolated situation where there's no recourse. They can't really come back home if they wanted to. So some people think it's going to be doomed for the psychological reasons, that it's just going to be so hard for anyone to be cooped up so far from home in a situation where they know that's the end of their life that they're facing. But I think the bigger concerns about it are just our technical concerns, that the delivery spacecraft, the technologies to establish viability of even a tiny colony within the time scale of 5 or 6 years are extremely aggressive and challenging. To make a comparison, NASA, which has its own plans for Mars colony, they're not really well funded, but they're well thought out. NASA certainly knows how to do these things too, and NASA is estimating that it would take 20 years to go from a first exploratory sortie to the most minimal colony. Mars 1 claims they're going to make that step in 4 or 5 years, which just sounds implausible, however much money they might have.
Okay, the next question that has quite a few votes is, if the universe is infinite, do we have infinite possibilities that somewhere exists a clone of our Earth with exactly the same people living on it?
Yes, in principle, this is one of the fun things you can do with math. Infinite is, of course, infinite, so it allows infinite possibilities. So what does it mean? What's the basis for this? I think the basis for this is, for example, going back to an earlier question, the measurement that space is flat. So we live in a flat space-time where the boundary of our vision is really just set by the distance we can see in the time light has traveled since the Big Bang. So we can only see in a direction about 46 billion light years in any direction, and that visible universe encompasses about 100 billion galaxies. What we say is beyond that is simply we don't know, but there's no reason to imagine that the flat space-time within that volume does not continue beyond the volume we can access with our telescopes. And since the Big Bang Theory, nor general relativity, nor any observation put any bound on the size of the universe, it is indeed possible that the physical universe, all that there is, as opposed to all that we can see, is infinite. So logically and scientifically, it's legitimate to talk about living in an infinite universe. We simply can't rule that out. We can't actually test that idea either. So if we live in space-time that could be extraordinarily large compared to 46 billion light years in any direction, and whatever that volume that implies, then what are the implications? Imagine that space is filled with galaxies that extend through this vast, possibly infinite region of space far beyond what we can see. And indeed, if you make the calculation, which you can do, there is some distance that I'll refer you not by the name of the paper, but to his website of the man who's done this in a slightly playful, tongue-in-cheek way, but he's also a very smart cosmologist, so the calculations are correct. Max Tegmark. He has a nice website with a lot of his papers and some more popular writings. Tegmark has done these calculations, so he's the one who actually calculated this, and he's a straight-up serious cosmologist. So he's calculated in an infinite universe with all the possibilities of evolution and rearrangement of atoms in different ways, how far you would have to go, to reference the original question, to find a clone copy of the Earth and everyone on it. In other words, a sheer replica of ourselves and our world. It's an extraordinary distance. I can't actually remember the number, but it's 10 to the power 10 to the power 37 or maybe 50. So that's a double exponent, which you have to sit and think about for a little while. So we're not talking about 10 to the power 37. We're talking about 10 to the 10 to the 37 light years, say. It's a number you can calculate based on the rearrangement of the possible number of atoms in all our bodies and the planet itself. It's clearly extraordinarily hypothetical. I'd almost call it a philosophical argument. But yes, to answer the question simply, indeed, in an infinite universe, all things must happen somewhere, including replicas of you and me and everyone on this planet. And in fact, Tegmark closes the discussion in one of his papers in an extraordinary way by saying how far you would have to go to find a direct replica of our entire observable universe, where all the 100 billion galaxies and all the trillions and trillions of stars and unknown forms of life on all those planets around those stars are identical too. At that point, it's starting to get silly then.
Okay, the next question that has a good number of votes is from James, and James asks, how far can you see with a good amateur telescope?
The best now are very good. It's such a variable landscape now, because telescope building, small telescopes, are in a renaissance, and that renaissance is really driven by the sort of point and shoot versions of the GPS that's now built into telescopes of more than a few $100s, which lets you tap in the name of an object, and so you don't have to figure out how to align your telescope, and you don't really have to know how to navigate the sky. And the purest amateur astronomers, of course, don't like that very much. They make it their business to know the sky. But to lower the bar or broaden the audience for using small telescopes and doing amateur astronomy, it's extremely valuable. So that's one innovation that's really opened it up. And the second, of course, is cheap CCDs. there's a CCD in every one of our cell phones taking pictures with the camera, and there were 1 billion of those CCDs sold in the world last year, which is a phenomenal number, essentially almost all in cell phones. Digital cameras themselves are a small part of the market now. So CCDs plus programmable telescopes where you don't have to know the sky have really opened this up. And so where is the bar on being able to see a significant depth? It's about $300 or $400. If you spend less than $300 or $400, the optics, the quality of the optics, which are really made of plastic, not glass, and the coatings, which are required to not have interior reflections or see a large wavelength range, you're talking about cheaper coatings, cheaper plastic, cheaper components in general, and so above that mark, you start to get higher quality optics, wider field of view, less internal reflections, and that helps the depth. Any of these telescopes, whether it's a Celestron or a Meade, or those are the two of the major manufacturers, will let you see roughly 100 times fainter than the naked eye. Naked eye sees to about 6 magnitude from the dark side. If your eyes are super good and you're at a super dark side, I've heard you can see 7th magnitude, and I don't know anyone who can do that, and I can't do it, but you're going to see another 5 magnitudes with a small telescope, and that's a lot. I mean, 5 magnitudes is a factor of 100 in depth, and in terms of distance, it goes as the inverse square, so that's 10 times the distance. 10 times the distance is 1,000 times the volume. So in principle, a small telescope is letting you see 1,000 times more stars than the naked eye. That's pretty impressive.
All right, the next question is about quantum mechanics and relativity. Quantum mechanics being so weird and defying our common notions, yet successfully explains numerous phenomena, but this theory doesn't reconcile with Einstein's theory of relativity. Can we ever unify these two major theories and get a theory of everything?
Huge question, of course. Important question for physics as well as astronomy. Maybe it's even more important for physics than for astrophysics. But the two are united in trying to get that kind of a theory. So way back from the dawn of the theory of general relativity, which emerged in 1916 from Einstein, and the quantum theory that emerged through the 1920s into the early 30s from Bohr, Heisenberg, and so on, this problem has existed. It was clear that the general theory of relativity deals with sort of, even though they may be curved, it deals with smooth, continuous space-times, whereas, and they're calculatable, they're quantifiable and smoothly calculated. Whereas quantum theory deals with probabilities, and it deals with discontinuous entities of energy and even time because of the quantized nature of energy states. So these are very distinct ways of thinking about nature between quantum theory and relativity. So even in the mathematics and in the way space and time and energy and mass are conceived of, it was clear these theories were not very like each other. The reconciliation of the theories, the other part that challenged the reconciliation was, of course, the vastly different fundamental strength of the natural forces. Of the 4 forces of nature, gravity is by far the weakest force, and the forces that determine quantum theory, the forces of the atom, the weak and strong nuclear force, are not just orders of magnitude stronger, they're tens of orders of magnitude stronger than gravity. Gravity is fantastically weak compared to these atomic forces or quantum theory rules. And nobody could conceive of a theory that could reconcile such disparate energy or temperature realms, as well as this difference between continuous nature and discrete nature. A huge challenge, and Einstein gave over the last 15 years of his life to the unification of his theory of gravity with the quantum theory. He also had his own beef or problem with the Copenhagen interpretation and some of the ways quantum theory had been thought about by physicists in the first half of the century. Einstein failed. He did some very interesting things, some very interesting experiments. You know, to be charitable, you could say that theoretical physicists peak in their late 20s, and he tried to do most of his work when he was in his 40s and 50s. So he was past his prime. Now, Einstein past his prime is better than almost anyone else at any point in their careers in physics, but he still did not succeed. And since then, it's been a bumpy road. We've had essentially 70 years of looking for a theory of everything. The most recent wave of activity really started quite a long time ago, in the 1970s. A series of physicists in the United States and the United Kingdom came up with theories which were the precursor of string theory. And this was an attempt to find a geometric theory of space that would somehow allow gravity to be unified based on tiny, tiny microscopic one-dimensional entities of extremely high energy density, strings. So string theory emerged in the 1970s, mid to late 1970s, and for a decade or so, it just was an oddity. It was an aberration, and only a small set of gravitational theorists and physicists could even understand it or work with the math. And so it didn't really get very far. It didn't seem to apply to anything. It was isolated. It was extremely difficult to work on. That started to change in the 1980s because string theorists made some significant progress. They actually started to see underlying unities in nature that could successfully underlie what was a very confusing zoo of subatomic particles. So still at a very mathematical level, string theory started to make some progress in the 90s. And after that, it started to hit another wall. The calculations were just very difficult. String theorists have still spent decades trying to reproduce normal results of quantum mechanics in string theory. It's that hard to do. So progress in string theory has been very, very slow, despite the brilliance of the people working on it. And that's led, in the last 5 or 6 years, to a backlash in the physics community, where some senior physicists, who may have been well disposed to string theory originally, have decided that we've been sold a bill of goods, or more importantly, that bright young physicists have been steered down this path where their chances of making a career or making a real discovery or an impact are slight compared to other things they might have worked on. So I'd say string theory, and therefore, since it's still the best candidate, the search for a theory of everything, is in a tricky and delicate stage. The people who work on string theory are still convinced that the beauty, elegance, and mathematical symmetry of the theory means that it's probably got some validity. And it has had some significant successes in tethering to the real world that we understand and describe with other theories. But it hasn't taken the mantle of a theory of everything. It hasn't swept aside quantum theory. It hasn't fully unified gravity and the quantum world in a neat package. Maybe that will happen, but this is going to be a long agenda.
So a related question from Wayne, and this probably will need to be our last question. Wayne asks, can you help an old brain grasp the concept of multiple dimensions beyond the 3 we live in plus time? Do we need to think in terms of 10 to 12 dimensions because the universe is expanding?
So we definitely need to think about 4-dimensional space-time. So in general relativity, space-time is a single construct. So you have your x, your y, and your z, and they can be curves, of course, in general relativity, and you have t as a time dimension. So that 4-dimensional unified construct is one entity, so we have to think about that. And of course, curved 3-dimensional space-time doesn't make any sense intuitively unless you were in a superior dimension with which to view it, just as we can't conceive of a curved 2-dimensional space easily if we lived on that space, like the surface of the Earth, but if we rise above it, we can see that it's curved in a higher dimension. String theory only worked, since we've just been talking about it, if the dimensionality of space-time was much more than what we experience in our everyday lives. Basically 8, 10, or 12-dimensional space-time. In the theory, those hidden dimensions are hidden because they're compactified onto an extraordinarily small physical scale and then an extraordinarily high energy scale. That's what it would take to realize those hidden dimensions. So that's a natural part of string theory, that it only works, the mathematics only works, if you function in these higher dimensions of space-time. And that's led to these offshoots of brain theory and other things you may have read about. The mathematics of it, which really is what underlies the physics, is completely reasonable and not that hard to work with. The mathematics of multidimensional curved space-time pre-existed general relativity by 70 years or more. There were Russian mathematicians in the mid to early 19th century. Bolyai, Lobachevsky are the two most famous ones, and not famous to most people outside mathematical physics, of course, but they were extremely brilliant at what they did. They were essentially mathematicians. They developed, working from much earlier ideas of Gauss and others, they developed the formalism of multidimensional curved space, even in anticipation or without any evidence that those higher dimensions had any physical meaning. And the mathematical formalism is self-contained, and you can take it up to any level. You can have 10, 20, 30, 54, 212 dimensional space-time, no problem. You can just scale or extend the mathematics, because the math will do that quite easily. The issue becomes, do these higher dimensions of space-time have any physical meaning? String theory posits that they do. String theory posits that the 3 dimensions of large, cold, and cold space-time in our universe are a relic of an initial state at the time of the Big Bang that embedded all these other dimensions that are now invisible to us because we live in a low-energy universe. And that, of course, is the $64,000 question. Can we find any verification that these hidden dimensions exist? And with that, I think we'll wrap up for today. Excellent questions as before, and we'll be back again next week.